See what I just did there? That's called the vertigo effect. As I increase the distance of the camera from myself, I also increase its focal length so that it's focusing more and more on me while revealing more of the background. This involves changing what is known as the camera composition, its distance from the subject and its focal length. The interesting thing is that different compositions can give vastly different results for the exact same scene and the exact same subject. But what if I only find the perfect composition after capturing the image? Or I want a physically impossible composition, such as getting something that's very far away from me to be right beside me. This is where Nvidia Research's computational zoom paper comes in. All it requires is a dolly-in stack of pictures. The first stage in their pipeline is multi-perspective imaging. Let's add another camera to the mix, call it camera 2, and have it be farther away, farther back, and with a larger focal length. If you notice, the fields of view of these two cameras intersect at a plane which we will call pi1. Now if we enforce a condition where anything that's beyond the plane we capture with camera 2 and anything that's behind it we capture with camera 1, we have what is known as a short-long configuration. But for this to work, we need to make sure that objects that are exactly on the plane pi1 map to the same pixel, whether mapped with the homography matrix of camera 1 or camera 2. To enforce this condition, we use what is known as a plane-induced homography matrix, which intuitively takes pixels on the image plane of camera 1, projects them to the plane pi1, and then projects those to the image plane of camera 2. And now, if you look at the equations here, where P1 and P2 are the homography matrices of camera 1 and camera 2, this condition holds. And we can easily expand this to include more cameras and more dolly planes for a more complicated system. However, this formulation requires us knowing the depth of every object in our photo. As a result, we also need to perform depth reconstruction. For the first step here, we use the patch match stereo algorithm to get depth and normal maps for every image in the stack. However, patch match only uses one image as a reference every time. Because of that, the depth values across all the images in the stack are inconsistent. Now, in a typical multi-view stereo pipeline, we would enforce consistency using the disparities between these different images. But here, we have a problem. The epipoles are not parallel lines. Instead, they go through the images. And as such, disparity is not really well defined for those epipoles and in the area around them. So we need to use other measures. Let's go back to our example. If I take a pixel from camera 1's image plane and I project it to camera 2's image plane using a plane-induced homography, and then I reproject it back to the original camera's image plane, I can check the pixels. If I get the exact same pixel, I have what is known as reprojection consistency. However, similar to what was discussed before, this will not be a good measure for points near the epipoles. As such, we can also look at how much this back and forth plane-induced homographies scale areas around the pixels that we care about. The idea is if I get a neighborhood with the exact same area before and after the reprojection, then I have scale consistency because the scales are almost or perfectly inverses of one another. Lastly, we have color consistency, which looks at the largest difference between any color channels at the pixel that we're interested in. Now, if we enforce this empirically found set of conditions on our plane parameters and they are satisfied for Q images in the stack, we say that the plane parameters are Q consistent. As you may imagine, this is not going to be the case for all the pixels in our stack. As a result, we need to run an iterative algorithm where we reduce Q and we find plane parameters that are consistent with those new values of Q. In the end, if there are any pixels that are still not consistent with any value of Q, we just propagate that information from nearby Q consistent pixels. Intuitively, what this is doing is this is distinguishing patches in the stack that are common and present in all the frames and those that are only present in a few frames, such as a random person running in front of the camera for a second or two. In the end, now that we have our depth maps and they are consistent, we can synthesize the image. For synthesizing the images, we need to respect epipole consistency, which states that the pixel value for a ray that hits the center of projection of any camera in the scene must be taken from that camera specifically. Now, in our case, what that means is for anything that's behind the plane, we take the pixel values from camera 1, and anything that's beyond the plane, based on the depth maps of either camera 1 and camera 2, we take those values from camera 2. Thanks for watching.